Another application of the student's T, other than what we talked about in the last lecture, in the last lecture we said one application of the student's T is to confirm using the confidence interval equation, where the true value lies. The confidence interval equation, has been repeated here. But another application of the student's T, is to compare a known value, to a measured value and confirm if they are very, very close. And so typically we use this when we are validating a method that has been developed and that is new, and you're trying to assess if that method is fairly accurate. Assume you go out there and develop a new method to detect, say, glucose in blood that is different from the conventional amperometric techniques, that are used. So typically you would run a data set using your analytical method, and you would buy a certified standard reference material and you run it using your new method. And then you would compare, the data from your new method with what the manufacturer says the standard reference material, has in terms of the concentration. So you're going to see how you do this is very similar, to the confidence interval equation, which is just an analogous method of doing it. So you do the T calculated, which is this T that you make it into the subject of the formula. And you can see this mu, that's the known value, minus the x bar when you take it to the other side of the equation sign, divided by the absolute standard deviation, which is this. We divide it on both sides, multiplied by the root of n. And based on the null hypothesis, where you take the measured value and using the null hypothesis, you indicate they are not any different, between the measured value and the standard reference material, and then you test that null hypothesis. So you would calculate the T calculated, based on this equation, and then you compare the T that you've calculated with the T, that you get from the table. And as you can remember, the T in the table, you just determine what confidence interval you want to use. The degrees of freedom based on the number of measurements that you took. And remember again, the degrees of freedom is the number of measurements that you took minus 1. And so you would come here and determine what is the T calculated. Now, if the T that you've calculated is less, than the T in the table, then the null hypothesis is valid. If, on the other hand, the T that you've calculated, is greater or equals to the T in the table, then the null hypothesis fails, which means that the two measurements are different. And so your analytical method is not giving you something close, to the true value. Now, let me give you an example, to try and, solidify what I've just said. What if you get a data set, that looks like this? You've developed an analytical method to analyze iron, say in water. And you've bought a standard reference material, and the standard reference material says that that sample has 5.85 nanometers. And using the method that you've developed, you determine that for that standard reference material, you are getting a number of 5.76 plus minus that relative standard deviation. And that one has been obtained from analyzing 10 times. So you would come and calculate the T. The known value, which is the 5.85, is a certified value, minus the determined value, divide by the absolute standard deviation, and then you multiply that by the root of the number of measurements. And as you can see, the t that you've calculated is 1.674. Now the t in the table, the degrees of freedom is n minus 1, and n is equals to 10, the number of measurements that were done. So the degrees of freedom is 9, and we are interested with 95% confidence interval. So if you come here on the table, the degrees of freedom is 9 and 95 confidence interval, and so the t that is calculated is 2.262. And so as you can see, the 2.262 is much bigger, than the t that you've calculated, and as such, the null hypothesis holds true. And so the t that you've calculated is much less, than the t that is in the table. And so the conclusion is your analytical method is good because it's giving you a number that is very, very close to the true value, meaning the true value is not different, from the experimental value. And that's what you tested in your null hypothesis. Maybe you can try this at home. You've got another set of data here. A chemist analyzes a sample of iron ore, that is furnished, by the National Bureau of Standards. Those are the organizations that make standard reference materials. And you get the following set of results, from your experimental method. Now, the NBS value, the value from the manufacturer, is 10.60. And so the question is your method valid? Are they giving you any different results from the true value? And so the question is, are the results significantly different at the 95% confidence interval? And so confirm the answer. Again, you just use a t-calculated, as I've shown you before. Feed in all the values and set up the null hypothesis. If the t-calculated is less than the t in the table, then the results are not significantly different. And in this case, you're going to see the t calculated was 5.06. The t in the table, same degrees of freedom as the last one, 9. And so in this case, it's 2.262. And so you can see the t from the table, is much smaller than the t you've calculated. And so the results in this case are significantly different, meaning your analytical method is not as good in doing the accurate measurements, of your iron ore. So other than determination of the confidence interval, we've already said you can use the student's t as an application in quality control charts. I've also explained that you can actually use it to determine if the measured value is different from the true value, of a reference standard. Now, another application is where you use the student's t to compare replicate measurements of two different methods. So you've got two methods and you want to compare them to see if they give the same results statistically. And that way you can choose any method. Remember, as an analytical chemist, one practical challenge that you will face is how do you choose one method over the other? There's always a cost implications. There's always how long it takes to do the analysis. There's always differences between analytical methods in terms of the usage of reagents and so on. And so sometimes you have to think, which is the best method to use between two? And so if at all you've got two types of data sets, you need to compare the two data sets from two different methods giving you very similar results. And that way you can look at other considerations then when you're choosing an analytical method. So when you're comparing two sets of data, maybe from two different analytical methods, you do the t calculated, using this equation, okay? So again, you know all the variables, and so you can feed the variables into that equation to do the t that you've calculated. Now in this case, we make an assumption that the two methods give you the same precision. So the S, the absolute standard deviation, is pooled. And the equation of pooling the standard deviation between the two methods, method 1 and method 2, is shown here. Now the degrees of freedom for two sets of methods, is going to be N1, meaning the number of repeats that you did for method 1, the number of repeats you did for method 2, minus 2, that's the degrees of freedom. And similar to what we did before, if the t calculated, is less than the t in the table, then the null hypothesis holds true. And so the two methods are very similar. They're giving you the same results. So maybe I'll give you an example here. You've got a sample of soda. You've got a sample of soda ash, and it's being analyzed, by two analytical methods, method 1 and method 2, and each one of them is giving you those respective results. Maybe method 1, you can think of it possibly as ICP, inductively coupled plasma. Maybe the other method, could be titration, just as an example. Okay? And so the question is, are the two methods significantly different at 95% confidence interval? Are these two results statistically different? That's what you're trying to evaluate. And so basically you use a t-calculated equation as shown, the x bar 1, that is the mean of method 1, mean of method 2, and so on. And so you can substitute all that into the equation. I think it's fairly straightforward. And you can do the S pooled using this equation. Now, the S1 is the absolute standard deviation for method 1, absolute standard deviation for method 2, and the rest are fairly obvious, the number of repeats, that's the N. And you can see the T that you've calculated is 1.491. And then the T from the table, with 7 degrees of freedom, is equals to 2.365. And so you can see that the T from the table is much larger than the T calculated. And so the null hypothesis is correct, meaning the two methods are not statistically significant. So remember, again, if the T calculated is less than the T from the table, then the null hypothesis holds true, meaning that the two methods are not statistically different. Now, in that problem that we just solved, we've assumed that the variances between the two methods are very similar. Now, that's not always the case. And so probably you should have first tested, are these two variances actually any different? Are these two variances different? Okay. And how do you do that? We test if the variances are different by using what we call the F-test. And so the F-test is used to compare two sets of standard deviations from two methods. And it's very similar, to what we've done with the T calculated. The null hypothesis is as follows. If the F calculated is less than the F from the table, so if the F calculated is less than the F from the table, then the null hypothesis holds true and the two standard deviations are not different. So how do you calculate, the F? Very, very simple. You just take the variance, the absolute standard deviation squared of method 1 divided by the variance of method 2. So the absolute standard deviation of method 2 squared. Remember, the F is always bigger than 1, meaning the numerator should always be the bigger number. So the S2 up here should always be the bigger number because the F calculated must always be 1. And then similarly, like the t-test, you come into the table based on the degrees of freedom, of method 1. The method at the top is the one that's up here. The method at the bottom, the denominator is here. And then you can determine, what the F calculated is. And if the F calculated is less than the F from the table that you determine, then the null hypothesis holds true. And the two variances are not different. If they are not different, then you can go ahead and do the S pooling, like I showed you before. So maybe I give you a set of data here from the previous example. S1 from the previous example was 0.1. The method 2, on the other hand, had an absolute standard deviation of 0.12. So you put it into the equation, the F calculated. As I say, the numerator has to be the bigger number. So the 0.12, divided by the 0.10. And so here you get the 1.44 as the F that you calculated. Now, to get the F from the table, remember the method 1 had 4 degrees of freedom. And method 2, had 3 degrees of freedom. So you come up here. Method 1 has 4 degrees of freedom. Method 2 has got 3 degrees of freedom. And so the F calculated, is 9. The F from the table. So you can see the degrees of freedom here for the method 2, the one that is at the top, is 3. The degrees of freedom, for method 1 it's 4. So you come here and check the t that is calculated. The one at the top, it's 3. And the one at the bottom, it's 4. And so the degrees of freedom is 6. The degrees of freedom is 4. And so the t that, the F that is calculated, is 6.5, is 6.59. And so here it is, 6.59. And so the F that is calculated, remember, it was 1.44, which is much, much smaller, than the F from the table. And so basically, the null hypothesis holds true. The two standard deviations are very, very similar, meaning the precision is very, very similar. And so the approach we used to pool the S pooled, remember, was accurate, because the two standard deviations are very similar. Now, in the event that the standard deviations are not similar, it means we shouldn't pool, the S. And so in that case, we should actually use this type of equation, where the t calculated is calculated as such, so you're not pooling the S. And the degrees of freedom in that case, we calculate it, as follows. As you can see, the equation may look quite ugly, but it's trivial in terms of just substituting, the S and the N for the respective analytical methods. So again, this equation, you use it if the two standard deviations are different, meaning you cannot pool them, based on what we just talked about in the F test. So the next thing that we're going to talk about is sometimes you've got a set of data and then you realize that one data set in your set of data looks like it's too different, from the others, and it's making your precision or the standard deviation poor. And so sometimes you wonder, should you omit that data, as an outlier? Now, you cannot just reject data just because it looks like it's an outlier. Instead, you have to do what you call the Q-test of any questionable data. And again, it's fairly straightforward. So again, if at all you find any data, that is questionable during your experiments in the lab, you must always do a Q-test. You cannot just reject it before you do a Q-test. And so the Q-test is done as follows. The Q calculated is equals to what they are calling here the gap divided by the range. And the gap refers to the difference between the questionable value minus, the value that is closest to it in magnitude, whereas the range, as the name suggests, refers to the difference between the largest value and the smallest value. And the null hypothesis again is similar. If the Q calculated, is much smaller than the Q from the table at a specific confidence interval, then you should keep the data. Hope it's very clear. If the Q that you calculate is less than the Q from the table, then you should keep the data. The data is not an outlier. If the opposite is true, then the data is an outlier. Okay? Give you an example here. You've got a set of data here. You've run it 5 times, and you've got this data set, for fluoride detection in water, 2.4, 1.98, and so forth. Now, looking at your data here, you realize that the 2.37 is way much farther, from these other data sets, from these other numbers. And so you want to do a Q test, of your 2.37. And so again, you can do the ratio, the 2.37 is a questionable data. And so the gap is minus the data that is closest to it. And as you can see, is a 2.08 is the data that is closest to it. And the range would be the largest data, which is a questionable data, minus the 1.87, that is the range. And when you do that, you get a ratio of 0.58. If you check from the table, we had 5 measurements, that's 5. And we are looking, at 90% confidence interval in this case. And so the Q from the table, you can see is 0.642, which is much bigger, than the Q that you calculated. And so you can see our null hypothesis holds true. And so we should actually keep the data. We should keep the data. The data is not bad. We should actually keep the data. So I'd like you at home, to try these 2 sets of problems, that are very similar to what we just covered. So try these 2 sets of problems at home. Now, lastly, we've talked about different types of errors. But I'd like to remind you that another type of error, that is very common when you're doing real sample analysis is what you call the sampling error. Now, remember where we went when we were talking about the analytical process. We said one requirement of the analytical process is to make sure that the sampling is representative. The sample that you get is representative, of the whole, because that's what you're taking to the lab. However, in cases where you're doing heterogeneous samples like solid sampling, becomes fairly tricky to get a good representative sample. And so in that case, you would expect, substantial amount of sampling error if at all you're doing a heterogeneous sample, meaning the composition of the analyte is not evenly distributed in your sample. So how do you determine sampling error? So the sampling error is basically determined, from this equation. Now, the measurement that you get in the lab is often a total error, coming from the sampling error as well as your measurement error. We've already said every measurement, has got some form of error. So that's what we're having here, the variance of the measurement and the variance of the sampling error. Now, because you already know the total error here, typically you can determine what the measurement error is. And how you do that is by running a very homogeneous sample. So you take a sample that is very, very homogeneous and you use your analytical method to run that sample. And so based on that, you would know the the total error, you know that, and so you can determine, what the sampling error is. Let me give you an example. So assume you're given this type of a data set. You've got a pure nickel standard that you run in the lab, possibly using a technique that we're going to cover in class, called AAS, atomic absorption spectroscopy, or even ICP, inductively coupled plasma. Now, you can run these sample, on any of these analytical methods. So this one is a pure standard that you make in the lab. You run it and you're getting, an average value of percent nickel as 99.972. So you can see that this is a homogeneous sample, meaning, that data that you're actually getting in this case, is coming purely, from, so meaning the data you're getting in this case, is coming from the measurement error, which is the SA, It's coming from the measurement error, which is the SA. And of course, you calculate the standard, deviation as you normally do. And when it's squared is what you refer to as the variance. Now, on the other hand, if you look at the other side, you analyze what you call the iron ore. Now, the iron ore, this is the true sample, okay? Meaning it's fairly homogeneous, or rather it's fairly heterogeneous, and so the sampling error, that is involved in this measurement. So this measurement is giving you the measurement error, but it's also giving you the sampling, the sampling error. And so this one becomes, the total error. So this number here is a total error, okay? And so based on that, then, you can actually calculate, what the sampling error is. So this is the error coming from the homogeneous sample. This is the error that is coming from the real sample, which is the ore, meaning it's a mixture of different things. And so if you take these to the other side, then you can calculate the sampling error, based on that relationship. And of course, you can take the square root, of both sides, so that you just get the absolute, or rather the relative standard deviation at the very end. So basically, that's how you determine, the sampling error. You run a homogeneous sample, and then you run the real sample, you get the standard deviation, and so whatever is left is just gonna be this, which you can determine as a sampling error. So lastly, just to remind you, remember the term paper topic is due on the 2nd of October. You should submit it on Blackboard. Remember the general theme, as I had said in the course outline, is going to be on wearable analytical devices for diagnostics of different things. And again, I said you can personalize your term paper topic based on what your career interests are. I had given lots of possible suggestions of what you can do. If you don't want to take any of the topics I had suggested in the introductory lecture, just choose your own topic, so long as it fits, in this theme. And then you're going to post it on Blackboard. I'm going to create an assignment link, called the term paper topic on Blackboard, where you're going to submit, your term paper topic, by the 2nd of October. If you're unsure about your topic, please send me an email and I can help you decide based on your career interest what's a good topic you can work on.